The morning of June 7th, 1944. Omaha Beach, Normandy, France. Commander Edward Ellsberg stood on the deck of a massive concrete caisson as it wallowed through the channel swells, spray breaking over the bow every few seconds. Around him, dozens more of these immense structures crawled toward the French coast at barely 3 knots, each one towed by straining tugboats that looked absurdly small against their concrete charges. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Ellsberg gripped the rail and watched the smoke still rising from the beaches ahead. Yesterday, 156,000 Allied soldiers had stormed ashore in the largest amphibious invasion in human history. Now came the harder problem. How do you keep them supplied? How do you land 2.5 million more men, 500,000 vehicles, and 4 million tons of supplies onto beaches with no port, no docks, no cranes, nothing but sand and the bodies of yesterday's casualties? The answer, improbable as it seemed, floated all around him. 2 complete artificial harbours, each the size of Dover, built in sections across England, towed across the Channel, and now being assembled off hostile shores, while German artillery still pounded the ridgelines inland. Military experts on both sides had declared the concept impossible. The German High Command had built the Atlantic Wall on the assumption that no invasion could succeed without capturing a major port. Their entire defensive strategy rested on that certainty. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. They were about to discover they had been catastrophically wrong. This innovation, dismissed by many as mad fantasy when first proposed, would make D-Day victory possible. It would allow the Allies to bypass the heavily fortified ports and land armies anywhere along vast stretches of coastline. Without it, Operation Overlord could never have happened. The entire strategy for liberating Europe would have collapsed. The story did not begin on the beaches of Normandy, but 3 years earlier on the blood-soaked shingle at Dieppe, where the Allies learned the hardest lesson of the war. August 19th, 1942. Dieppe, France. The sun rose over the English Channel to reveal a catastrophe unfolding along the French coast. Canadian soldiers of the 2nd Infantry Division lay dead and dying on the beaches, caught in withering machine gun fire from German positions on the cliffs above. Churchill tanks sat immobilized on the shingle, unable to climb the steep beach gradient, burning under direct artillery fire. Landing craft burned in the surf. The raid that was supposed to last a day and gather intelligence had turned into a slaughter within the first hour. By 10:50 in the morning, Allied commanders ordered a retreat. By mid-afternoon, the battle was over. Of the nearly 5,000 Canadian troops who had landed that morning, more than 900 lay dead. Another 1,874 had been captured. 68% casualties for an operation that achieved almost none of its objectives. The Dieppe raid stands in history as one of the great disasters of World War II. Yet from that disaster came a realization that would shape the entire future strategy of the Allied war effort. Vice Admiral John Hughes Hallett, who had helped plan the operation, stated categorically after the raid that capturing a defended port would be impossible in any future invasion. The Germans had proven they could turn any harbour into a killing ground. Port facilities could be demolished faster than they could be captured. Any invasion force that depended on seizing a port in the opening days would be trapped on the beaches, unable to sustain itself, and ultimately driven back into the sea. If a port could not be captured, then one would have to be brought. This seemingly impossible conclusion led directly to the most audacious engineering project of the entire war. Winston Churchill had actually been thinking about portable harbours since the First World War. In 1917, when he served as First Lord of the Admiralty, he had sketched plans for using sunken caissons filled with sand to form an artificial breakwater off the Dutch coast. The proposal had been shelved and forgotten as events moved on. But Churchill never entirely let go of the idea. His mind, always searching for unconventional solutions to military problems, kept returning to the concept of bringing one's own harbour to the fight. On May 30th, 1942, just months before Dieppe, Churchill issued a memo titled Piers for Use on Beaches. The memo, characteristically direct, outlined the problem with brutal clarity. Any cross-channel invasion would require massive supply operations. Ports would be heavily defended. Beaches offered no facilities for unloading ships. Therefore, the Allies needed to construct their own facilities and bring them across the Channel. The memo landed on the desks of Britain's most capable engineers and military planners. Most regarded it as fantasy. Build an entire harbour, transport it across the Channel, assemble it under fire on an exposed beach? The technical challenges seemed insurmountable. The resources required appeared beyond even British industrial capacity, already stretched to breaking by 3 years of total war. The weather and tides of the Channel presented problems that seemed to have no solution, but one man had already been thinking along exactly these lines. Hugh Ioris Hughes, a 39-year-old Welsh civil engineer, had submitted his own proposal to the War Office just weeks before Churchill's memo. Hughes knew harbours. More importantly, he knew the sea. Raised in Conwy on the North Wales coast, he had grown up sailing the treacherous waters of the Menai Strait with his father and brothers. He understood tides, currents, storms, and the brutal forces that the ocean could unleash on man-made structures. Hughes had studied engineering at the University of Sheffield, then joined the consultancy of Owen Williams, one of Britain's most innovative designers of concrete structures. For 15 years, Hughes worked as resident engineer on some of Williams's most notable projects. He supervised construction of the original Wembley Stadium. He managed the building of major bridges in Scotland, including the Findhorn Bridge and Montrose Bridge. He learned to work with reinforced concrete on massive scales, creating structures that had to withstand enormous stresses. More than technical skill, Hughes possessed the rare combination of practical seamanship and structural engineering expertise. He could visualize how concrete would behave in seawater, how structures would respond to tidal forces, how to design systems that could flex and move rather than rigidly resist the ocean's power. When war broke out in 1939, Hughes found himself in a reserved occupation. His engineering skills were considered too valuable to the war effort for him to join the armed services. Instead, he worked from his London offices on various war-related projects, but his mind kept returning to a problem he knew Britain would eventually face. How do you land an army on a hostile shore that has no port facilities? In the spring of 1942, Hughes sat down and began sketching. His designs showed massive reinforced concrete caissons, hollow structures that could be floated across the Channel, then sunk in position to form a breakwater. On top of these sunken caissons, he proposed steel bridge spans that would create roadways from ship to shore. The roadways could carry vehicles, tanks, and supplies directly from the holds of cargo vessels onto the beach. The system would create an artificial harbour where none existed, allowing ships to unload in sheltered water regardless of tides or weather. Hughes signed his drawings, I, Iris Hughes, M.E., and submitted them to the War Office on June 17, 1942. The package included 9 detailed pencil drafts showing every aspect of his proposed system. General layouts, cross-sections of the caissons, calculations of buoyancy and stability, details of how the spans would connect to create continuous roadways, construction methods that would allow the massive structures to be built in sections and assembled at sea. The War Office filed the proposal away. One more idea from a civilian engineer who didn't understand the realities of modern warfare. The military had its own people working on these problems. What could a bridge builder from Wales possibly contribute that professional naval architects hadn't already considered? But Hughes had one crucial advantage. His brother, Commander Sir Hughes, served in the Royal Naval Volunteer Reserve. Through his brother's connections and his own persistence, Hughes managed to bring his plans to the attention of people who understood their revolutionary potential. As Churchill's memo began to generate serious interest in artificial harbours, Hughes's designs suddenly became relevant. By late 1942, the War Office had established a committee to coordinate work on what was now being called the Mulberry Project, after the next available codename on a long list. The project pulled together multiple teams working on different aspects of the problem. The Royal Navy's Directorate of Miscellaneous Weapons Development worked on breakwater designs. A transportation unit designated TN5 handled overall planning and coordination. Civil engineering firms across Britain competed for contracts to build various components. In early 1943, the War Office ordered the construction of prototypes for testing. Hughes received authorization to build full-scale versions of his caisson and roadway system. The construction site chosen was Conwy Morfa, near Hughes's hometown, an enormous flat area that could be turned into a massive outdoor factory. Within weeks, Conwy Morfa had been transformed into one of the largest construction sites in Britain. Over 1,000 labourers worked around the clock. Concrete mixers roared. Steel reinforcing bars were bent and tied into massive cages. Wooden formwork rose higher each day as the first caissons took shape. Hughes supervised every detail, checking calculations, inspecting welds, ensuring that the structures would survive both the journey across the channel and the punishment they would receive from ocean waves once in position. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. He designed his caissons, which he codenamed Hippos, to rest on the seabed once flooded. The largest measured 60 feet long, 17 feet wide, and stood as tall as a 5-story building. They displaced 6,000 tons when flooded with seawater. The reinforced concrete walls were thick enough to withstand direct hits from artillery fire and the constant battering of waves. Compartments inside could be selectively flooded to control how the structure settled onto the seafloor. On top of the Hippos, Hughes designed steel bridge spans he called crocodiles. These would connect the sunken caissons to create a continuous roadway from deep water to the beach. The spans had to be strong enough to support fully loaded tanks and trucks, yet light enough to be transported in sections and assembled at sea. They had to flex with the movement of the caissons beneath them without buckling or cracking. The engineering tolerances were extraordinarily tight. By early summer 1943, Hughes had completed 3 full-size Hippo caissons at Conwy Morfa. Each represented months of work and tons of precious materials, steel and concrete that were desperately needed elsewhere. The structures sat in the shallow waters of the Conwy River estuary, connected to shore by temporary roads. Workers could walk inside the massive hollow chambers, their voices echoing off concrete walls designed to withstand the full force of Atlantic storms. Now came the test that would determine whether Hughes's vision was engineering genius or expensive folly. The caissons had to be towed over 200 miles of open water to Garliaston in Wigtownshire, Scotland. There, in Wig Bay, the military had established a secret testing facility. The bay's characteristics closely matched those of the Normandy beaches: flat, sandy, remote, and sparsely populated. A security cordon had been established. Local inhabitants had been moved away. The entire area from Garliaston through to the Isle of Wythorn was declared off-limits. A military camp at Cairnhead housed the hundreds of engineers and support workers involved in the testing program. The journey from Conwy to Garliaston tested the caissons in ways that no amount of calculation could predict. The massive structures had to be carefully refloated, a delicate operation that required precise control of ballast to prevent capsizing. Tugboats then towed them up the Welsh coast, around Anglesey, through the treacherous waters off the Isle of Man, and finally into the sheltered waters of the Solway Firth. Hughes rode with his creations, monitoring every phase of the journey. The Hippos wallowed through the swells, occasionally shipping water over their tops when waves broke against their blunt faces. But they remained stable. The concrete held. The reinforcing steel did its job. After several anxious days, all 3 caissons arrived safely at Rig Bay off Garliaston. At Garliaston, Hughes's Hippo system would compete against 2 other designs. Alan Beckett, a young naval engineer, had designed a floating roadway called Whale, consisting of flexible bridge spans mounted on pontoons that rose and fell with the tide. R. M. Hamilton had developed the Swiss roll, made of canvas and steel cables. All three systems would be constructed and tested under realistic conditions. Only the best would be selected for use in the actual invasion. The testing began in late summer 1943. Each system was assembled in the bay and subjected to the full range of conditions it would face in actual combat. Ships approached and attempted to unload cargo. Tanks and heavy vehicles drove across the roadways. Engineers measured stresses, deflections, and load capacities. Everything worked perfectly, at first. Then the weather turned. A fierce storm swept in from the Atlantic, bringing winds and waves that exceeded even the worst-case scenarios the engineers had planned for. For 2 days, the artificial harbour systems took a savage beating. Waves crashed over the structures. Wind tore at exposed components. The ocean demonstrated, with brutal clarity, exactly what any artificial harbour would face off the Normandy coast. When the storm finally cleared, the Swiss roll had been completely destroyed, washed away as if it had never existed. Hughes's Hippo system had suffered catastrophic damage. The waves had scoured sand from around the base of the sunken caissons, causing them to tilt. Once tilted, the rigid crocodile spans connecting them had cracked and failed. The entire system lay partially collapsed, testament to the ocean's power to destroy anything that tried to resist it rigidly. Only Beckett's Whale roadway had survived undamaged. The floating design had ridden out the storm by moving with the waves rather than trying to resist them. The flexible spans had twisted and bent but had not broken. The pontoons had stayed afloat. As the storm subsided, the Whale roadway settled back into position, ready to continue operations. The lesson was clear and painful. Hughes had been right about using sunken caissons for breakwaters, structures that needed to resist the ocean's force. But his rigid roadway system couldn't handle the constant movement of working in tidal waters under storm conditions. The flexible design had won decisively. For some engineers, such a failure might have ended their involvement in the project. Hughes responded differently. Rather than defending his failed system, he immediately recognized the superiority of Beckett's design and threw his considerable expertise behind making the overall Mulberry project succeed. The War Office kept him on as a consultant, particularly for work on the breakwater caissons that would protect the floating roadways. His engineering calculations and his understanding of how concrete structures behaved in seawater proved invaluable. Hughes's Hippo design was modified into a new version, code-named Phoenix. These caissons were even larger than the Hippos, with the biggest displacing 6,400 tons. But the fundamental concept remained Hughes's: massive hollow concrete boxes that could be floated to Normandy, then sunk in position to form a protective wall against ocean waves. By late 1943, the Mulberry project had reached an almost unimaginable scale. A committee of civil engineers, led by Brigadier Bruce White, coordinated the efforts of over 45,000 workers at construction sites scattered across Britain. Major construction firms, including Balfour Beatty, John Laying and Son, Taylor Woodrow, Sir Robert McAlpine, and dozens of others received contracts for different components. The sheer quantities of materials boggled the mind. The Phoenix caissons alone required 330,000 cubic yards of concrete. 31,000 tons of steel went into their construction and reinforcement. 1.5 million yards of steel shuttering formed the moulds into which the concrete was poured. The total amount of concrete used in the Mulberry harbours equalled roughly 13 million cubic metres, an amount that Nazi architect Albert Speer would later note exceeded what Germany had used to build 2 years' worth of Atlantic wall fortifications. Hastily constructed dry docks appeared along the Thames and Clyde rivers. Existing shipyards converted to building concrete caissons instead of steel ships. Sites at Richborough in Kent, Southsea, Southampton, and Marchwood hummed with activity. Each location specialised in different components. Some built Phoenix caissons, others fabricated the steel roadway sections. Still others constructed the Beetle pontoons that would support the Whale roadways. Specialised workshops produced the massive winches, anchors, and towing equipment needed to move and position the structures. The work proceeded under intense secrecy. German reconnaissance aircraft photographed the construction sites and the growing fleet of strange concrete structures collecting in British harbours and estuaries. Fortunately, German intelligence could not figure out their purpose. The structures looked like nothing in any military inventory. Speculation ran wild in German headquarters. Were they new types of submarine pens? Some kind of coastal defence? The truth, that they were complete portable harbours to be towed across the channel, lay beyond what German planners considered possible. Security around the project was extraordinarily tight. Workers were told only what they needed to know for their specific tasks. Few understood how their piece fit into the larger picture. The codename Mulberry appeared on no documents that might fall into enemy hands. Even among the Allies, only those with the highest security clearances knew the full scope of the operation. The engineering challenges multiplied as the project grew. How do you calculate exactly how much concrete you need to sink a caisson of A, specific size to a specific depth on a seabed of unknown composition? How do you design roadways that can carry 60-ton tanks while floating on pontoons that rise and fall 21 feet with each tide cycle? How do you connect rigid steel spans to flexible floating supports without creating stress points that will fail? Every problem required innovation. Engineers developed new calculation methods. Builders invented new construction techniques. Welders perfected methods for joining steel underwater. Naval architects designed specialized vessels for towing the massive caissons. Every specialty involved in construction, every discipline within engineering, contributed expertise to solving problems that had never been encountered before. As winter turned to spring in 1944, the components began to assemble. Phoenix caissons sat moored in harbours and estuaries around Britain, their massive concrete hulls riding low in the water. Steel roadway sections lay stacked on docks. Beetle pontoons crowded harbours. Old merchant ships and obsolete warships, designated gooseberries, were prepared to be deliberately sunk as additional breakwaters. An entire fleet of specialized tugboats assembled, ready to tow the artificial harbours across the channel. By May, 2 complete Mulberry harbours sat ready. Mulberry A would go to Omaha Beach in the American sector. Mulberry B would be installed at Gold Beach, supporting British and Canadian forces at Arromanches. Each harbour, when fully assembled, would equal the cargo handling capacity of the port of Dover. Each would have multiple piers with a combined length of 6 miles. Each would be able to handle 7,000 tons of supplies per day, moving from ship to shore, the military designated D-Day for early June, dependent on tides and weather. On June 4th, the fleet assembled for the crossing, but severe weather forced a postponement. General Dwight Eisenhower, Supreme Commander of Allied forces, faced the agonizing decision of whether to proceed with less than ideal conditions or delay further, possibly for weeks, until the next favorable tide cycle. On June 5th, his chief meteorologist forecast a brief window of acceptable weather. Eisenhower made the call. The invasion would proceed on June 6th. At approximately midnight, the largest armada in human history began moving toward France. Over 7,000 naval vessels, including roughly 4,000 landing craft and 1,200 warships, crossed the channel, and at the rear of this enormous fleet, moving at barely 3 knots, came the artificial harbours. Hundreds of tugboats strained against their tow lines, pulling the massive Phoenix caissons through the dark water. Other tugs towed sections of pier, roadway spans, pontoons, bombardons, every component needed to build 2 complete harbours on hostile shores. The crossing took most of the day. Meanwhile, on the beaches ahead, the first waves of assault troops were going, ashore at 6:30 in the morning. Men waded through chest-deep water under machine gun and artillery fire. Some beaches, like Utah, went relatively well. Others, like Omaha, turned into a bloodbath. By day's end, approximately 156,000 Allied troops had landed in Normandy. Casualty figures would eventually reach over 10,000 killed, wounded, or missing. As darkness fell on June 6th, the artificial harbour components began arriving off the coast. Naval construction battalions, known as Seabees, and Royal Engineers took over, working around the clock to assemble the structures while battles still raged inland. On D+2, just 2 days after the initial landings, the first Phoenix caissons were positioned and sunk. By D+7, 1 week after D-Day, the harbours had begun limited operations. The achievement bordered on miraculous. Under fire, in exposed waters, military engineers were constructing 2 complete harbours larger than most of Palm, Britain's peacetime ports. Tugboats positioned the massive Phoenix caissons with incredible precision, creating breakwaters that calmed the water inside. Gooseberry blockships were deliberately sunk to supplement the caissons. Whale roadways were assembled and connected to shore, creating highways over which tanks and trucks could drive directly from ships to the beach. Within 12 days of D-Day, both Mulberry harbours were operational. Port Winston, as the British harbour at Arromanches became known, was handling thousands of tons of cargo daily. WWII at Omaha was coming online rapidly, though still not at full capacity. The impossible had been achieved. The Allies had their ports, exactly where they needed them, assembled under the noses of a German army that still didn't fully understand what had happened. Then, on June 19th, nature delivered a brutal reminder that the Channel could destroy human works regardless of their scale or importance. On the evening of June 19th, 1944, 13 days after D-Day, the wind began to rise off the Normandy coast. By midnight, a full gale was blowing from the northeast, the worst possible direction. Waves that had been manageable swells transformed into walls of water crashing against the artificial harbours with devastating force. The storm that hit Normandy that night was the worst to strike the coast in 40 years. For 3 days, winds reached force 6 and 7 on the Beaufort scale, creating conditions that the Mulberry harbours had been designed to withstand, but only barely. The timing could not have been worse. Both harbours were still being reinforced and strengthened. Many components had not yet been properly secured. The structures were at their most vulnerable. At Omaha Beach, WWII bore the full brunt of the storm. The American harbour was less complete than its British counterpart and more exposed to the open sea. As the wind howled and waves battered the structures, engineers watched helplessly as their work began to disintegrate. Ships broke loose from their moorings and crashed into the Phoenix caissons. The concrete structures, each weighing thousands of tons, began to crack under the repeated impacts. Bombardons, the floating steel breakwaters anchored outside the main harbour, tore free from their moorings and drifted away. By the morning of June 20th, the destruction at Omaha had reached catastrophic levels. 21 of the 28 Phoenix caissons had been completely destroyed, shattered by colliding ships or undermined by scouring currents. The whale roadways lay smashed, their pontoons capsized or sunk, their steel spans twisted into useless wreckage. Hundreds of smaller vessels had been driven onto the beach or sunk in the harbour. The carefully constructed artificial port, representing months of planning and construction, had been reduced to debris in a single night. Lieutenant General Omar Bradley, commander of the United States 12th Army Group, came down to inspect the damage on June 23rd when the storm finally subsided. "I was appalled by the desolation," he wrote later, "for it vastly exceeded that on D-Day. The comparison was telling. The storm had caused more physical destruction than the German defenders had managed during the invasion itself. The loss of WWII represented a potential disaster for the entire Normandy campaign. The original plan had called for the port at Cherbourg to be captured by June 21st, just 15 days after D-Day, but Cherbourg remained in German hands. The defenders were resisting fiercely, and when the port finally fell on June 27th, the Germans had demolished the facilities so thoroughly that it would be months before significant cargo could be unloaded there. Without WWII and without Cherbourg, American forces faced the prospect of being unable to sustain their advance inland. At Gold Beach, Port Winston had fared better, though it too had taken severe damage. The British harbour was slightly more protected from the northeast winds by the configuration of the coastline. More importantly, Many of its Phoenix caissons had been pumped full of sand after being sunk, giving them far greater stability than their American counterparts. This simple modification, implemented based on lessons learned during the assembly process, made all the difference. The whale roadways at Arromanches flexed and twisted in the storm, but did not break. Alan Beckett's flexible design, which had won the competition at Galveston, proved its worth under the most extreme conditions imaginable. The pontoons rode up and down with the massive waves. The steel spans bent and groaned but held together. When the storm passed, the roadways settled back into position, damaged but functional. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Hugh Iris Hughes worked frantically throughout the storm and its aftermath to save what could be saved. The decision was made to abandon WWII and concentrate all efforts on keeping Port Winston operational. Salvageable components from the American harbour were towed to Arromanches to reinforce the British installation. Phoenix caissons that had survived at Omaha were refloated and repositioned at Gold Beach. Spare roadway sections replaced damaged spans. The harbour that had been designed to last 3 months would now have to sustain Allied operations indefinitely. The reinforcement work proceeded at a furious pace. Engineers pumped sand into additional Phoenix caissons to increase their stability. Extra anchoring systems secured the whale roadways. Damaged sections were repaired or replaced. Within days, Port Winston was not just operational again, but actually stronger than before the storm. The British harbour, reinforced with components from both installations, became the primary supply point for the entire Allied beachhead. The statistics of what Port Winston accomplished in the months that followed demonstrate why the Mulberry concept, despite the loss of one harbour, must be counted among the decisive innovations of the war. In the first week after the storm, with the harbour still being repaired, 74,000 troops, 10,000 vehicles, and 17,000 tons of supplies came ashore through the damaged facilities. By the end of June, just 3 weeks after D-Day, over 289,000 tons of supplies had been offloaded through the Mulberry harbours and directly onto the beaches. The daily tonnage increased as operations became more efficient. The objective had been to handle 3,000 tons of stores per day by D-Day plus 7,000 tons, and 2,500 vehicles by D-Day plus 8, and finally 12,000 tons and 2,500 vehicles per day at full operation. Port Winston exceeded these targets. On good weather days, the harbour handled cargo at rates equivalent to major peacetime ports. From June 15th to 18th, before the storm struck, a total of 15,774 British and 18,938 American troops landed every day through the two harbours, along with an average of 2,000 vehicles and 25,000 tons of stores. These figures represented the realization of every planner's goal, proof that artificial harbours could actually work under combat conditions. After the loss of WWII, Port Winston carried the entire burden over the next 10 months until the port was finally closed in November 1944. It facilitated the landing of 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. These were not theoretical calculations or optimistic projections. These were actual tons of cargo, actual vehicles, actual soldiers who came ashore through a harbour that existed only because engineers had imagined the impossible and then built it. The Mulberry harbours demonstrated a principle that would shape military logistics for decades to come. An invading force no longer needed to capture existing port facilities. Given sufficient engineering resources and imagination, an army could bring its own infrastructure with it. The implications went far beyond D-Day. Any future amphibious operation could employ similar techniques, creating artificial harbours wherever they were needed. But the human cost of developing this capability had been enormous. The Dieppe raid, which had convinced Allied planners that artificial harbours were necessary, had cost over 3,000 Canadian casualties for an operation that lasted less than a day. The workers who built the Mulberry components laboured in dangerous conditions, often under threat of German bombing. Some died in industrial accidents at the construction sites. Others were killed when German aircraft attacked the assembly areas in England. The men who assembled the harbours in Normandy worked under even more hazardous conditions. German artillery continued to shell the beaches throughout the assembly process. Luftwaffe aircraft strafed the construction areas. Naval engineers worked on exposed structures in all weather, knowing that a single misstep could send them into the cold Channel water. The Seabees and Royal Engineers who built Port Winston under fire demonstrated the same courage as the infantry fighting inland, though their weapons were welding torches and sledgehammers rather than rifles. For Hugh Iris Hughes, the Mulberry Project represented both vindication and humility. His original Hippo design had failed the Garlieston tests, unable to survive the storm that destroyed the Swiss roll and proved the superiority of Beckett's whale. A lesser engineer might have walked away, pride wounded, contribution dismissed. Instead recognized that engineering excellence required the ability to admit failure and adapt. His Phoenix caissons, refined versions of his original concept, formed the breakwaters that made the harbours work. His calculations and expertise contributed to solving countless problems during construction and assembly. Yet Hughes received little recognition during his lifetime for his contributions to D-Day's success. While generals had battleships named after them and filled history books with their exploits, the Welsh civil engineer who had submitted the first working designs for artificial harbours remained largely unknown outside professional engineering circles. He was not appointed to the official committee that oversaw Mulberry construction, despite his early submissions and prototype work. His name appears in few popular histories of the war. The credit for Mulberry went to committees, to military organisations, to the general concept rather than to specific innovators. This pattern of obscurity extended to many of the Mulberry engineers. Alan Beckett, whose whale roadway design survived the June storm and made the harbours functional, received more recognition than most, but still far less than his contribution merited. Brigadier Bruce White, who coordinated the massive construction effort, remained unknown to the general public. The 45,000 workers who actually built the components laboured in anonymity, their names lost to history even as their work changed the course of the war. Part of this obscurity stemmed from wartime secrecy requirements. The Mulberry Project remained classified long after D-Day. Details of how the harbours were constructed, how they worked, and who had designed them could not be widely published while the war continued. By the time restrictions were lifted, other stories had captured public attention. The dramatic battles, the heroic infantry charges, the air combat, these made for compelling narratives that overshadowed the technical achievements that made victory possible. But the Allied commanders who directed the war understood perfectly well what the Mulberry harbours had accomplished. General Dwight Eisenhower, in his post-war memoirs, wrote that the artificial harbours represented one of the most crucial innovations of the entire European campaign. Without them, he noted, the strategy of landing anywhere along the French coast, rather than concentrating on heavily defended ports, would have been impossible. The flexibility that Mulberry provided allowed Allied planners to choose the weakest point in German defences, rather than attacking where the enemy was strongest. British Prime Minister Winston Churchill, who had pushed for the artificial harbour concept from the beginning, took personal pride in the Mulberry achievement. In his multi-volume history of World War II, he devoted considerable space to describing how the harbours were designed, built, and deployed. Churchill understood that wars were won not just on battlefields, but in factories, drawing rooms, and engineering offices where innovative solutions to seemingly impossible problems took shape. The German perspective on the Mulberry harbours provides perhaps the most telling assessment of their importance. Albert Speer, Hitler's Minister of Armaments and War Production, made a remarkable admission after the war. "To construct our defences," Speer said, referring to the Atlantic Wall fortifications, "we had in 2 years used some 13 million cubic metres of concrete and 1.5 million tons of steel. A fortnight after the Normandy landings, this costly effort was brought to nothing because of an idea of simple genius. As we now know, the invasion force brought their own harbours and built at Arromanches and Omaha, on unprotected coast, the necessary landing ramps. The phrase "simple genius" captured exactly what made the Mulberry concept so revolutionary. The idea itself was not technically complex. Hollow concrete boxes to form breakwaters, floating roadways to bridge the gap between ships and shore. Old vessels deliberately sunk for additional protection. None of these individual components required breakthrough technology or scientific advances. The genius lay in recognizing that these elements, combined and scaled up to unprecedented size, could solve a problem that had seemed insurmountable. Germany's entire defensive strategy for the Atlantic coast had rested on the certainty that invaders would need to capture a major port quickly. The Wehrmacht concentrated its best troops and heaviest fortifications around ports like Cherbourg, Le Havre, Calais, and Boulogne. Hitler personally issued orders emphasizing that these port cities must be held at all costs, understanding that losing port capacity would doom any invasion. Coastal defense batteries, infantry positions, minefields, obstacles, all were positioned on the assumption that the Allies would have to come, straight at the ports. The Mulberry harbours allowed the Allies to simply bypass this entire defensive system. Instead of attacking where Germany was strongest, Allied forces landed on relatively lightly defended beaches between the major ports. They brought their own harbour capacity with them. By the time German High Command fully understood what had happened, over 1 million Allied soldiers had come ashore with all their equipment and supplies. The Atlantic Wall, which had consumed 2 years and massive resources to construct, had been rendered strategically irrelevant in 2 weeks. The success of the artificial harbours validated an approach to amphibious warfare that would shape military operations for decades. During the Korean War, similar techniques were employed to create temporary port facilities. In Vietnam, floating piers and artificial harbours supported operations where existing infrastructure was inadequate or controlled by the enemy. Even in more recent conflicts, military engineers have drawn on the lessons learned from Mulberry when establishing supply lines in hostile or underdeveloped coastal areas. Beyond purely military applications, the Mulberry project demonstrated what could be accomplished when engineering expertise was fully mobilized for a national purpose. The scale of organization required to coordinate 45,000 workers at dozens of construction sites, to allocate scarce materials efficiently, to solve countless technical problems under extreme time pressure, all of this provided lessons that extended far beyond warfare. Post-war infrastructure projects in Britain and throughout Europe employed organizational methods developed during the Mulberry construction effort. The project also demonstrated the value of accepting failure and learning from it. Hughes's Hippo design failed at Galveston, but that failure led to improvements that made the Phoenix caissons more effective. The June storm destroyed WWII, but the lessons learned from that destruction allowed engineers to reinforce Port Winston so effectively that it lasted 8 months, despite being designed for only 3. At every stage, engineers confronted problems they had not anticipated, adapted their designs, and found solutions. This iterative approach to problem-solving, testing ideas under real conditions and modifying them based on results, became a model for complex engineering projects. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.